Here we have our surge impedance loading limits. So typically for very long lines, your power flow must be limited to what is commonly called the surge impedance loading, your SIL, of the line. The SIL is going to be equal to the square of the end of the voltage divided by the characteristic impedance of the line. So since the characteristic impedance of various high voltage and extremely high voltage lines are not dissimilar, the SIL is going to depend approximately on the square of the system voltages. Typically, the stability limits may determine the maximum allowable power flow on the line that are more than 150 miles in length. For very long lines, the power flow limitation may be less than the SIL. Stability limits on the power flow can be as low as 20% of the line's thermal limit. And your SIL is your natural loading. So that's going to be your active power loading, your watts of the transmission line, where the reactive power is neither producing or absorbing. So to explain a little bit further, if you have your power flow in a very long transmission line, there's an electrical phase shift. So that's going to increase with your distance as the power flows. And as a phase shift increases, the system in which the line is embedded is going to become increasingly unstable and more open to electrical disturbances. So, more on the surge impedance. The value of the impedance load which causes no reflections is called the line surge impedance, or your Z0, your characteristic impedance, your ZC. The active power developed in such a load is called the line surge impedance loading. Its value can be calculated through the following. So this is your typical one-line diagram. And we have our I load is equal to VAN over the Z0, which is also equal to the VAB over the square root of 3 times Z0. Our SIL is going to be equal to radical 3 times VAB times VAB divided by radical 3 Z0, which is all equal to our VAB squared over the Z0. And these are all the surge impedance loading, which would be calculated in watts. So your characteristic impedance can also be calculated as your XL times the square root of your XL times your XC. So when your R line is equal to 0 and your G line is equal to 0, it's very important. And a couple other ways you can calculate your characteristic impedance depending on what you're given in your scenarios. You have the radical of Z divided by Y, or the radical of L divided by C.